Okay, so this will be our third EM class of the Paragon X EM course. Uh, Today we're going to be talking about conductors and capacitors. Uh, Before that, let's just first go over the homework. Let's see. Oh yeah, this is our class structure, so we're going to start by reviewing the homework. Um, so it will be great to have students do the homework that's assigned every week. If you have any ideas on how to solve the problems or questions, just feel free to email it to me or Shamik, and we'll try to get back to you as soon as possible. And yeah, try to ask as many questions as you can because it will really help you learn the material. Um, right, so this was the first homework problem. A thin plastic semi-ring of radius r has a uniform linear positive charge density lambda. Determine the electric potential V at point O, which is the center of the semi-ring. Okay, Charles, do you have any idea on how to do this problem?
Oh, sorry, I wasn't here last time, but
Oh yeah, don't worry. Yeah. Did you get a chance to review the recording?
I have not.
Oh, it's all right. Okay. I'll just go over this homework problem then. So let's draw a picture. Uh, Semi-ring. Okay, so let's see. I'll draw the semi-ring like a semicircle, and it has uniform linear positive charge density lambda. So as lambda, and determine the electric potential V at point O, which is the center of the semi-ring. Okay, so right, so we want to find electric potential, and remember that if we have a point charge, so if I have a point charge like Q, and then I'm at a distance R away from it, so I'm at a point P, and this is distance R away from Q, then the electric potential at point P due to charge Q will be KQ over R. And if I have multiple charges, so for example, if I have another charge over here, that's like as charge big Q, and it's a distance big R away, then the electric potential at point P would be the superposition of the potentials due to both charges. So the potential at P would be KQ over R plus the potential due to big Q, which would be K big Q over big R. So we can apply this superposition principle to this problem. So um, in total, the total charge on the semi-ring, that's going to be lambda times pi r. So I'll write that as Q total. Q total is lambda times pi r. And notice that if I'm looking at an infinitesimal segment of the semi-ring, each of it will have a like if it's an infinitesimal segment of lambda ds, then the total charge on it would be lambda ds, right? And the potential um due to each infinitesimal segment, that'll be lambda ds divided by the radius of the semi-ring, right? So lambda ds divided by the radius of the semi-ring, which I'll call big R, and times k. And then I want to do the integral of this over the entire semi-ring. And notice that here, big R, lambda, shoot, big R, lambda, and k, they're all constants. So this integral is just going to be k lambda, uh, k lambda over R, integral of ds. And that's just k times lambda I big R divided by um big R, right? So the potential would be K lambda times pi. And notice this is the same thing as doing K times Q total divided by big R. You're getting the same answer. And so this will be the electric potential at the center of the semi-ring. Now let's move on to part B. Do you have any questions on part A?
No, not really.
Okay, good. Um, all right, let's do part B. Find the magnitude and direction of the electric field E at point O. All right, so let's draw the diagram again, or I'll draw a better one. All right, so I'm looking at point O, and now what we're doing right now is we're finding the electric field E at point O, and all right, so this will be slightly trickier. Uh, the reason is you'll see. So I'm at point O, and then say I'm looking at an infinitesimal segment over here of length ds, right? So it has charge lambda times ds. And now when we're doing electric field, right? So if I'm looking at this, if I'm looking at, yeah, that infinitesimal segment, that will cause the electric field to that segment at point O, it will be in this direction. And notice if I look at maybe like over here, that causes that generates an electric field that's in this direction, right? And so you can see that like if I go across the entire semi-ring, then like this is what the electric fields due to each infinitesimal segment will look like, uh, so on. And then you'll find that the horizontal components cancel and the net electric field would be in this direction. So let's actually get quantitative and solve the problem. So if I'm if I'm looking at, you know, this is an angle of theta, then I know that, okay, the electric field here, like, it'll be uh lambda ds, which is the charge, right, times k divided by big R squared, right? And this would be in this direction. But since I know that the horizontal components will cancel, when I do the integral of the electric fields, um, I go over the when I integrate over the semi-ring, I only need to care about the vertical component because the horizontal component will cancel. So the vertical component of this would be, you know, if I draw this triangle, this would be theta, right? So it will be k lambda ds over big R squared uh times the sine theta. So, and this would be an infinitesimal electric field. And now, uh, notice that I have a theta over here, but the variable here is ds. So when I do the integral, I need to change ds into d theta. And you know that if I have like a circle and I'm looking at over here, there is an infinitesimal, there's an infinitesimal angle of d theta, then this arc length over here, this would be, shoot, I'll draw it better. Uh, this over here, that's going to be r times d theta. So that means that that equals to ds. So I'll replace this ds over here with big R d theta. So then let me erase this over here. When I do the integral, when I want to find the total electric field, I'll be integrating that. So E would be integral of K lambda times sine theta, so sine theta. And then notice that this R cancels, so divided by big R, and then d theta. And our integrating boundaries would be from theta equals 0, so like from here all the way to theta equals to pi, right? So 0 to pi. And then all you have to do is just solve the integral. And I think you'll find that, okay, this will be uh negative k lambda cosine theta divided by uh big R and then evaluated at 0 and pi, right? So if you do that, then you'll be getting uh I believe you'll be getting 2k lambda times cosine theta and then divided by big R. So this will be your electric field. Let's move on to part C. Part C is it's not as complicated as this part. So remember we found the electric potential V at point O, right? And remember the definition, the like the equation to relate the potential energy and the potential, right? So I know that potential energy U would be the Q times the potential V. Now also, I know that U that equals to the negative work done to like bring a charge from infinity to a point, right? So I already found what V is um in part A, right? So all I have to do is just work would be the negative Q times the V, and you'll be getting your answer for part C. This is just a conceptual question. Yeah. So do you have any questions on problem one?
No, not really.
All right, sure. Let's go on to the next problem then. All right. The equipotential lines in a certain region of space are shown in the diagram above. Which of the vectors shown best represents the location and direction of the maximum electric field in the region? Okay, so we're given the potentials. So, equipotential lines, what that means is that along, like, for example, this line over here, all points on that line have a potential of 30 volts. And, on this line, 20 volts, and then on this line, it will be 10 volts, right? Now, recall the definition of potential. We had okay, potential V, that's equal to the negative integral. So if I, okay, if I'm looking at the potential change between 2 points, so like delta V between 2 points A and B, I'll be doing the negative E dot onto the ds from A to B. And okay, so for example, if I go from point A over here to point B over here, right? So I'll be integrating, so it's like I'll be integrating along this path. Uh, yeah. So I'll be integrating from point A to point B of this, right? Now, for example, if I instead look at from like over here, so I'll call this A uh A prime and B prime. Now, okay, I know that this potential difference between these two lines, I know that it's always 10 volts, right? Because I'm given this line has 30 volts and this is 20 volts. So from A to B and from A prime to B prime, the change in voltage is always like 10 volts. So if I know that it's 10 volts, then how do I find the electric field, right? So again, let's look back at this definition. Notice that from A prime to B prime, the total distance that you're integrating. Like so once you integrate, you're like, you have the ds over here, right? So like let's assume like that the electric field is constant across or like let's assume that the electric field is constant from point A to point B and from point A prime to B prime, right? Then I'll know that from V from A to B, that'll be um that'll be like like if I call that if I call this distance to be like DAB, right? And then times the E from A to B. And similarly, that would equal to the change in voltage from A prime to B prime, right? So d A prime to B prime times E of A prime to B prime. And then notice that, dA prime B prime, that's smaller than DAB. So that means that for those two quantities to be equal, I need E A prime to B prime to be greater than E A B, right? So no, if I have 2 points and they're close together, and I'm looking at the voltage between the two, and I know that it's the same voltage difference between 2 points that are far apart, then I know that the electric field over here should be greater than the electric field over here. And so if we now look at what they're asking us, so we want to find direction of the maximum electric field in the region. Well, over here, let me clear up some drawings. Yeah, so in this region over here, the equipotential lines, they're spaced closer together than over here. And what that means is that the electric field in this region, so, in the region of point C, that's greater than the electric field in regions like B, or like in this region and in this region. So we want to find the location and direction of maximum electric field in the region. So the answer would be C. Uh, yeah, because the spacing between the equipotential lines is the smallest. Do you have any questions on that or anything need me to like go more into detail?
Uh, yeah, I think you can move on.
All right, sure. Uh, yeah, just let me know if you don't understand anything, and I'll slow down. Yeah. Okay. Electric field in a region of space is given by function Ex equals 20x plus 10, where x is in meters and E is in volts per meter. What is the electric potential at x equals 2 meters relative to the origin? Okay, this is just a simple application of, remember, we have formula for potential. If I let infinity to be the place where potential is zero, then will be negative integral from infinity to x of the E dot onto ds. So 20x plus 10 and then dx, right? So this is just a simple integral that you can do. Uh, yeah, know your, just know the fundamental definition of the potential and just be able to do this integral. It's pretty standard. So you'll be getting negative 10. So the integral be negative 10 x squared minus 10 x from, oh shoot, my bad. Wait, was relative to the origin, so I'm actually letting this be zero. Letting wait, sorry, my bad. So I need to find like relative to the origin. That means that I'll be integrating from x equals zero because that will be the place where uh I'm setting the potential to be zero. So the boundaries will be from 0 to 2, right? Because yeah, I want the electric potential equals 2 meters, so this will be um negative 410, I believe. So negative 410. volts. Just remember, the lower boundary would be the place where you're doing the potential relative to, and the upper boundary would be the place where you're finding the potential at. And inside is just electric field, and don't forget the negative sign on the outside. And yeah, do you have any questions on this part?
No, I get it so far.
All right, good. Uh, let's see. All right, electric potential diagram below shows equipotential contour lines for a two-dimensional region of space, at which point A, B, C, or D would an electron have the highest electric potential energy. Yeah, so just remember U equals QV. So yeah, so um right, U equals QV, meaning that if you have a higher V, then it's a higher potential energy. And it does seem like the electric potential is increasing this way, so the electric field would be in this direction. Um, so yeah, so I just want to find the point with the maximum V. So that would be at point D because it has the most positive uh potential, right? Because you might think this place is where you have the highest potential energy, but that's the most negative potential energy. Here it will be at point D it will be positive. And what direction does the electric field point in this diagram? So remember, the electric field is always perpendicular to the equipotential lines, and the electric field points in the direction where the potential is decreasing. So here, potential is decreasing in this direction, right? Um, so the electric field would be like at any point it will be perpendicular to equipotential line and pointing like towards the left or like around approximately towards the left. So maybe here or if I'm looking over here, it will be probably pointing in that direction. So yeah. Uh conceptual problem. Yeah. Any questions on that or yeah.
No,
All right. Oops. All right. My last homework problem. 3-point charges produce the equipotential contour lines shown in the diagram below. Draw arrows that points L, N, and U on the diagram to indicate the direction of electric field at those points. Well, this is just basically the same problem as last time, as the last problem, because remember, uh, so the potential is decreasing as I go that way. So at L, it would be perpendicular to the equipotential line, so that way. At point N, maybe in this direction, and point U be in this direction. And at which of the letter points is the electric field E greater than magnitude? Well, this is actually the same as a problem, one of the previous homework problems we discussed. So remember, a smaller spacing between the equipotential lines means a greater magnitude of your electric field. Calculate an approximate value for the magnitude of the electric field E at point P. So just remember, if the E is constant, then V, I can say it's going to be equal to the E times the distance between the 2 points. And yeah, it does seem like we're given a scale here. We can just like, no, this is probably from an AP test. So you can just like use a ruler, measure the distance between the two, and measure like, find the change in voltage between 2 points. And yeah, this really is like if I were to have no time and have to do just one problem, then I would do this problem because it's just a summary of like the all the other homework problems that we went over. Uh, all right. Oh, no questions, or do you have any questions? Aaron and Ryan and Charles, do you guys have any questions? Or yeah.
I'm good for now.
All right. Uh, if you guys have any questions, just let me know in the chat. Yeah. All right, let's start our lesson. Give me a second. All right, so today we're going to be talking about conductors and capacitors. So let's first talk about conductors. Uh, yeah, so conductors, the property of conductors is that charges can move freely in them. It's not like an insulator. So for example, you might have heard like, you probably have heard if you have a wire and you can have a current that goes through it, right? So in a wire, the charges, they're able to move through them. So you can say that wires, they need to be conductors. Otherwise, if they're insulators, charges can't move through them, right? So yeah, um, a path of conductors between the object and the Earth's surface serves to ground the object. So basically what that means is that if I have a conductor over here and yeah, and I have the Earth over here. Now, if I attach a wire from the conductor to the Earth, and let's say the conductor originally had some charge on the surface, then what would happen is that all of this charge on the conductor, it would move through the wire and into the ground. And um, just remember, and that's because the Earth is actually a really, really big conductor. So if I attach a wire to the ground, what the charges will do is they will flow through the wire and they'll go into the earth because the earth is it's a really big conductor. Uh, in static conditions, the electric field equals to zero inside an isolated conductor, and all charges reside on the surface. Yeah, so uh, the V for the voltage for a conductor is constant across the conductor's surface. And the reason for that is, if I have like in a static situation, so this might be my conductor, it can be like shaped however I want. If the charges are static, that means that they're not moving, right? So the charges, they can only move across, like if they're moving, they move along the surface. Now, if I had, for example, if at a point over here, my electric field was in this direction, so it's not perpendicular to the surface. That means like if I decompose it into components, then it has a component that's along the direction of the surface of the conductor. So if I placed a charge over here, then that means the charge, like there's a force exerted on the charge that makes the charge go in that direction. And that's not allowed if it's a static situation because that's a contradiction. The charges cannot be moving, which means that if I'm in a static situation, then the electric field, they can only be perpendicular to the surface of the conductor. Because if they're perpendicular to the surface of the conductor, the charges won't be able to move. And because they're perpendicular to the surface of the conductor, if I'm trying to find the voltage difference between, like, for example, from here to here, both points like A and B, and I want to find the voltage difference between the two, well, my path would be, for example, it would be if I integrate like that, um, and I integrate my path along the surface of the conductor, well, there will be no electric field in the direction of my paths, which means that the voltage at point A and point B, they're the same, which means that the voltage for a conductor is constant across the conductor's surface if I have a static situation. Yeah. So this is just some properties of conductors that you should uh, be able to like have a solid grasp on. And it's mainly conceptual stuff, and we'll probably be tested on these on like the AP or like some other physics exams. If you want to read more or like learn more in depth about conductors, you can always look at, for example, there's a textbook I sent in my first email called um, Wong and Ricardo. So Wong and Ricardo, and I sent their electromagnetism textbook. Uh, there's a lot of like mathematical stuff, but if you look at chapter 6 in the Wong and Ricardo book, and you can read like just the first section of conductors, and it will give you like a very detailed rundown of like, conceptually what conductors are and like their properties. So if you want to learn more about that. Yeah, so let's move on. Capacitors, yeah. So capacitors will be a big part of our class today. So capacitors, they're like a piece in the circuit, and they're sort of like resistors. We're gonna be learning about circuits later in this course, but you probably have heard of circuits. Uh, Capacitors is it's one of the pieces in a circuit that we can put. And the purpose of a capacitor is to store charges. So what a capacitors look like is I have two plates and they're separated by some distance. Now, those two plates, they're both conductors, and which means that they're able to store charge and well, okay, if they're an insulator, they can also store charge, but uh thing is they are conductors, okay? And their purpose is to store charge. And it has a property which is called capacitance, and it's measured in um farads, which is just the same as charges per volt. Uh, so yeah, you have Q equals CV. This just comes from the definition of what we call capacitance. We'll just define capacitance C as Q over V. And you can notice that if it has a higher capacitance, that just means that the capacitor is able to store more charge. And yeah, wait, I'm giving you this formula over here, but I'm gonna show you a derivation of it in the next slide. So just remember, a capacitor is just consisting of two parallel plates, and uh, yeah, its purpose is just to store charges, and it's used in a lot of situations in real life, so they're pretty important. Yeah, derivations. So let's draw our parallel plate capacitor again. I have two parallel plates over here, and um, this has a charge Q, and this has a charge of negative Q. And okay, so electric field will be looking like, assuming that the parallel plates are infinitely large, which, it's not always true, but it's a good approximation. The electric field lines would be looking like this, right? Ignoring the fringe effects, like what would happen at the edge of the capacitor. This is what the electric field would look like. And you might be asking, why is there no electric field on, like outside of the capacitor? And the reason for that is, um, let me erase my electric field lines for a second. If I make like a Gaussian enclosure, so for example, remember Gauss's law, right? So if this is my Gaussian enclosure, then the total enclosed charge is zero, right? Because this plate has charge Q and this plate has exactly the negative Q, like exactly opposite amount of charge. So that means that if like the enclosed charge is zero, that means there's no flux. So our integral of E dot onto dA, that should be zero, right? Now, also, I know that inside the capacitor, this is what the electric field lines look like. So like that. That means there's no flux that goes through the side face of the cylinder, and the only flux, if there was flux, would be through these two faces. But thing is, there's no flux that goes through it, and I know that the electric field would be zero outside the conductor, so this would be equal to zero. Yeah, so that's why, if you're curious, there are no electric fields outside the capacitor. Uh, right. So now let's prove that formula for finding the capacitance. Uh, so if I draw my Gaussian enclosure, for example, if I draw, uh, let's see, All right, draw this in yeah, okay. I'll draw an enclosure that looks like this. So it would be sort of straddling the plate, and it's a cylinder, so uh like that. Now, wait, let me just redraw that because it doesn't look that good. Right, this is uh what my Gaussian enclosure would be. So it sort of looks like a pillbox. Um, and then so what is the enclosed charge in it? Well, the enclosed charge, like let's say it's just like this is my Gaussian surface, Gaussian enclosure, and then my plate would be going through it like that. So this has an area A, right? Uh, or yeah, sure. I'll say it has area small a, then the enclosed charge Q. So Q enclosed equals to uh yeah, that equals to A times sigma, right? A times sigma, and then I know that electric field would be looking like this, right? Going through that way. Now, then I know from Gauss's law, right? If I do the integral of E dot onto the dA, well, so I know the E is constant, right? So I pull the E out of the integral. E is also perpendicular to dA. So that means E times the integral of dA, which would be like A, that equals to Q enclosed over epsilon zero, right? So A sigma over epsilon, which means that my E would be equal to the sigma over epsilon. Now, and notice that this E, it's constant anywhere in this region between the two parallel plates. And if I want to find the voltage difference between the two, right, that means that the V would be equal to the sigma times the D divided by epsilon. And yeah, so I want to find, right, this is my V, and I know, we had that Q equals to the C times the V. Now, what is Q, right? So if the plate has an entire area of big A, right? So then what that means is that sigma times A divided by V, that will be equal to the C, right? So if I do that, then I'm getting, uh, so let me erase this. Oh, right. So sigma A over V, well, that means that C would be equal to sigma A times epsilons over sigma D, and this means that this equals to epsilon A over D. And uh that is how you find the capacitance of a parallel plate capacitor. And if I go back to the previous slide, yeah, we're getting the same thing. Or actually, oh wait, this is wrong. Uh, Ignore what was on that slide, but this is the correct answer for the capacitance. It should be epsilon A over D. And just remember the overall way of how I derived this was just draw this Gaussian enclosure and that straddles the one plate of the capacitor. Find the electric field inside the region between the two plates and find the potential, which is just the electric field times the distance between the two plates. And then because I define capacitance as the Q over the V, then I'll be able to find what the capacitance is. Um, does anybody have questions on this derivation? Because like this might have been a bit hard to understand if it's your first time seeing it. Um, but if you don't get it, don't worry about it. Um, you'll be able to review it later on, and it's not really that important. Like this is a bit advanced and it's not really required for you to know it, but it's really helpful to know it. So I'm not getting any questions, so I'll just move on to the next part. Let's see. All right, here's an example. Random access memory chips are used in computers to store binary information in the form of ones and zeros. One common way to store a one is to charge a very small capacitor. Of course, the same capacitor without charge represents a zero. A memory chip contains millions of such capacitors, each coupled with a transistor that acts as a switch to form a memory cell. A typical capacitor in a memory cell may have a capacitance of 3 times 10 to the negative 14th farad. If the voltage across the capacitor reading a 1 is 0.5 volts, determine the number of electrons that must move on the capacitor to charge it. Uh, okay, so just some background. I'll let you guys do it, but if you don't know what the charge of an electron is, just say that charge of an electron is just let it be, just let it be small e, just like yeah. And I'll give you guys a couple of minutes to do this. Just yeah, remember that. Yeah, just remember Q equals to CV, and yeah, I'll let you guys do the problem. Yeah, if you have any answers, you can just you send them to me in the chat. Okay, I'll just go over this problem because it's pretty standard. All right, so okay, I know I'm given the capacitance and I'm also giving the voltage, right? So I know that the amount of charge would be the capacitance times the voltage, which would be so this times this, which would be 1.5 times 10 to the negative 14th uh negative 14th coulomb. And so the number of charges, so number E would be equal to 1.5 times 10 to the negative 14th coulombs divided by the charge of an electron. So yeah, pretty standard application of the Q equals CV formula. Yeah. So this is charge and divided by the charge of an electron, you're getting at 93,750 electrons. So let's go on to the next slide. All right, so yeah, so always consists of two conducting plates, and yeah, after we'll learn circuits, we'll find what the charge on the capacitor as a function of time. You'll find that once a capacitor is fully charged by a battery, no more current will be flowing. Yeah, let's do this example. It's a bit complicated. You have a capacitor which consists of two concentric conducting spheres, and they each have a charge. So the inner one has a charge plus Q, and the outer one has a charge minus Q. And I want to find the capacitance of this. And just remember, C equals Q over V. So yeah, you know what Q is, so it's all about finding V. And this will be a conceptual application of what you should know about conductors. So I'll give you guys a few minutes to do this. All right, so I'll just go over this problem now. Um, oh yeah, Sing. So right now we're just gonna go over this problem. Uh, so this problem is about if you have two conductors, and they're concentric conducting spheres. They're hollow, and they both have, so the inner one has a charge of positive Q and the outer one has a charge of negative Q. And this forms a capacitor. Now, I want to find what is the capacitance of this capacitor. So just recall that, remember, we have for a capacitor, and this works for any capacitor, no matter if it's like parallel plate or spherical capacitor, that Q would be equal to uh capacitance times the potential difference uh between from like the first plate or like from here to here in our case. So I know what the charge Q is, right? Like we're given that that's Q. So we just want to find what the potential difference from the inner sphere to the outer sphere is. So that's basically what we're trying to find in this problem. And uh, notice that, okay, if I want to find the potential difference between uh, the two spheres, what I can do is I can first find the electric field in the region, like over here, and then I can do, remember, we have that potential difference is negative integral from like A to B of the E dot onto the ds. Okay, so let's try to find the electric field first. Uh, well, okay, these are two concentric conducting shells, and they each have charge. Oh, the inner one has charge positive Q, the outer one has charge negative Q. But remember, by the shell theorem, I know that in the region within the large sphere, I know that the electric field due to this large sphere within it, it's zero by the shell theorem. So if I'm looking at this region over here, the only contribution to the electric field would be due to this inner conducting sphere. And also I know that like another part of the shell theorem is that because this is a sphere, right? Then I know that I can reduce the inner sphere to just a point charge at the center. So I'll draw it out. So originally okay, we had this is positive Q and this is negative Q. Then if I wanted to find the electric field, for example, over here, it's within the outsides, it's within the larger sphere, meaning that the larger sphere does not, like there's no contribution to the electric field. That means the only contribution to the electric field is due to this inner sphere over here. So if I return back to this drawing over here, if I'm, for example, at that point over there, and I want to find the electric field there, and it's at a distance of r prime from the center, I can change this positive Q over here to a positive Q over here, and I can ignore the outer shell, meaning that the electric field at this point P over here, so E at point P, that would just be equal to the K times the big Q divided by the R prime squared. So if I wanted to find the potential difference between like here and here, well, okay, I have this formula, right? So then V would be equal to negative integral from small r to big R of K big Q divided by R prime squared, right? And then dr. So this is just equal to K big Q divided by R prime and then evaluated from small r to big R. And this is equal to, shoot, it's just K times Q divided by uh wait, yeah, K times Q, uh and then uh 1 over the big R minus 1 over the small r. And this is equal to the potential difference. So this is our V. And I know that C is equal to the Q over the V. So that means that C would equal to, I do Q divided by this, right? So I'll be getting 1 over the K times 1 over the big R minus 1 over the small r. And remember that K equals to 1 over 4 pi epsilon 0. So this will be 4 pi epsilon 0 divided by the 1 over the big R minus 1 over the small r. Yeah, this should be our final answer. Uh, if anyone has any questions on that, feel free to just ask the question in like the chat or interrupt me. Uh, both of those are fine. So yeah, uh, yeah, 1 over small r minus 1 over big R. Uh, I mean, okay, you can write it as this or the negative of this, as long as you get the idea that, you're doing Q over Q C equals Q over V, and just use the shell theorem to find, I don't need to care about the outer shell. I only care about the inner shell. And I can easily find the electric field at the region between the two shells. And yeah, I'll integrate the electric field to find the voltage and I can find the capacitance. So that's the overall idea of that problem. So let's move on. Oh, all right, capacitors in parallel. When we learn circuits, we'll go over this in more detail when we learn circuits. But the idea is if you have a circuit and like consists of maybe I have like if I have attached a battery over here and then I have many circuits in what's called like parallel, you might have heard this before, then I can replace this. This is equivalent to having like I have a battery over here and I put a single capacitor here, except it has the capacitance of the sum of all of the capacitors, of all of the capacitances. And if you want a proof of that, well, let's do this. Okay, so I know that the voltage across each capacitor that equals to the charge divided by the capacitance. And right, so that means each, yeah, so each capacitor, so like V equals C, like for example, CI. Okay, for like if I'm looking at the ith capacitor in parallel, and notice that this V is the voltage difference from here to here, right? And that's like the voltage difference across each capacitor, it has to be the same. Um, and I know that CI, right? CI, that's equal to the QI, the charge on the ith capacitor divided by the V. So if I do, it means that if I want to replace this by one capacitor, then I know that like if I do sigma of both sides, then I know that sigma CI would be equal to sigma QI over V, right? And then so that means that I can replace all of these capacitors in parallel with one single capacitor. It has charge of the sum of all of the charges and has capacitance of the sum of all of the capacitances. Don't worry if you don't get this, we'll be going over it again when we're learning about circuits. Uh, yeah, and similarly, if we have, oh yeah, so that was what we did. Capacitors in series, okay, and we can do a similar derivation. So, we have that okay, again, we have Q would be equal to CI, uh, VI. This time, the charge on each capacitor is the same. And the reason for that is, for example, I have this is my first capacitor. Uh, this has like Q and negative Q. Uh, yeah, right. So the next capacitor here will have to have the same amount of charge. So yeah, the charge on each capacitor has to be the same, and the capacitances and the voltage across each capacitor, that does not have to be the same, meaning that if I have VI equal to Q over CI, so if I do sigma both sides again, then notice that now I have the capacitance is on the denominator, meaning that I can replace this entire thing, the entire capacitors, the entire like group of capacitors in series with just one capacitor, except it has charge. Um, it still has the same charge Q on one plate and Q on negative Q on the other plate, except this time the equivalent capacitance will be like the reciprocal of the equivalent capacitance would be the sum of all the reciprocals. So yeah, what this is saying. Yeah. Uh, does anybody have any questions on that? Okay, if not, then I'll just move on. Uh, let's see. All right, practice series and parallel. Find the effective capacitance as well as the charge and voltage across each capacitor. Uh, if you haven't learned circuits before, this is going to be a bit challenging. So I'll just go over it so that yeah, so that it won't be too hard. So okay, we have yeah, these two are in series. So this one and this one, sorry, those two are in parallel. But first, we need to look at these three capacitors that are in series, right? So remember, I can replace this because these are in series, then I'll replace it instead with just one capacitor has some charge Q and negative Q on the plate and the equivalent capacitance, right? So 1 over C would be equal to 1 over like 1 over 6 plus 1 over 6 plus 1 over 6, right? Or 6. And you'll find that so that equals 2, right? So the equivalent capacitance, so C would be equal to uh 0 0.5. Oh shoot, sorry. 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 Okay, 1 over C. Okay. 1 over C is 1 over 6 plus 1 over 6 plus 1 over 6, which equals to 1 over 2. So that means the C would be equal to 2. So I'll replace this by it has capacitance of 2 microfarad. And I can further replace this, these are two capacitors in parallel. So I'll replace this with, instead, I'll put a 6 microfarad capacitor. So it has 6 microfarad. Right, now that means that the effective capacitance we solve for that's 6 microfarad. Now, what is the charge and voltage across each capacitor. Okay, right. So remember, um, I initially, okay, let's go back to I when I have this, right? So I have uh yeah, I have two capacitors in parallel. So that means that if okay, I know this is 100 volts, so then I can find total charge Q, right? That would be equal to 100, and then remember 100 volts divided by, yeah, 100 volts divided by the total capacitance, right? So we replace this with 6 microfarad, so 6 microfarad, and that was the total charge. And right, so we found that that was the total charge, and you can also find that, across this, right? So then for this one, because I know it's 100 volts, then yeah, so the Q for this one, let me clean this up a bit. For this one, the Q would be the C times the V, right? Sorry, this shouldn't be. Okay, so the charge on this 4 microfarad capacitor, that'll be 4 microfarad and then times the 100 volts, right? And yeah, you can find what that is. Just easily compute that. And also, I know that charge on this, right? On this 2 microfarad, that'll be 2 microfarad times 100 volts. Now, remember this 2 microfarad we got that after we replaced these three capacitors in series. And we know that like when we replace this with one equivalent capacitor, we had it replaced with the equivalent capacitor, and each plate had a charge Q, or like we had one plate with charge Q and one with negative Q. Now this Q, because it's in series, uh, it's the same Q that's on each of these capacitors. So this is also Q, this is negative Q, and so on, right? So this quantity over here, 2 microfarad times 100 volts, that's the same as the charge on each capacitor. So yeah. So then like after you find the numbers, you can just find what the charge and voltage across each capacitor was. So yeah. Let's go to the next problem. It's okay if you didn't get it. We'll again, like this is circuits, and we'll be going over it again in the future. Yeah. So nope. All right. Energy stored in a capacitor. All right. So yeah, I'll just go over this one. Um, yeah, I'll go over it quickly because we're running a bit low on time. So remember, we had like you, okay, we can say that like infinitesimal work done. This is by definition of what we call potential. So dW, that's equal to VdQ, right? So yeah, if we replace it like this, this is by definition of Q equals CVs, right? So we have this dW equals this. So if we do the integral of both sides, then like I'll do integral over here, right? So then total work done, that'll be equal to, or this should be total potential energy. Same thing, pretty similar. Okay, so that'll be Q squared over 2C. And how are we able to get these? Well, that's by replacing, for example, I know that Q equals to CV. So that means that the potential energy also equals to CV squared over 2. I also know that C equals to Q over V. So this also equals to Q V over 2. That's just the energy stored in a capacitor. Yeah. All right, dielectrics. So what dielectrics do? What are dielectrics? Well, dielectrics, they're just I originally had a capacitor, like for example, it's a parallel plate capacitor. What I do is instead of the region inside being a vacuum, I place a dielectric inside, which is an insulator. And what the dielectric does is it changes this epsilon over here. So epsilon is like uh changes, yeah, it changes epsilon. And what that does is it allows the capacitor to store more charge. So the epsilon zero is replaced by k times epsilon zero, which would be like some new epsilon, right? And remember, I had capacitance originally equal to epsilon zero A over D, right? Once I placed an insulator or like a dielectric in between the parallel plates, this epsilon gets changed and it increases to like for example, if I call it K epsilon times A over D. And what this does is it increases the capacitance, meaning that I'm able to store more charge if I fix the voltage, right? So dielectrics, they're used a lot to just increase the capacitance. And basically what it does is it replaces the region between the two capacitors, the two parallel plates. Instead of having just vacuum, I have an insulator in there. So yeah, it weakens the electric field inside. Uh, yep. So, just like if you ever encounter like shoot, sorry, if you ever encounter problems involving dielectrics, just an easy way to do them would be instead of like we had formulas like you saw epsilon zero a lot, right? So just to replace the epsilon zero with epsilon, for example, instead or like epsilon zero times k. So instead of the capacitance being epsilon zero A over D, you have capacitance is K times epsilon zero A over D. So yeah. Now here's some practice problem. A parallel plate capacitor is created by placing two large square conducting plates of length and width 0.5 meters facing each other, separated by a 1 centimeter gap. A source of potential is connected to the two plates so that a charge of Q equals sigma A is placed on the left plate and a charge of negative Q equals negative sigma A is on the right plate, where sigma equals 500 times 10 to the negative 6 coulomb per meter squared. The potential source is then removed from the plates. The plates are close together, so the electric field fringe effects at the edges are negligible. In the space below, draw electric field lines in the vicinity of the plates. Yeah, so when it says electric field fringe effects at the edges are negligible, just assume that these two parallel plates, um, you can treat them as infinite plates because the distance between the two plates is so small. So I'll give you guys uh a bit of time to work on that problem. Yeah. Yeah, I'll just go over this now because it's pretty standard. So remember, uh, there will be electric field lines running that way. Remember, we went over this when we did the Gaussian surface that straddles the that straddles the conducting plate. So you can get a better visual right now. There will be no electric field that's outside of the capacitors. There's only electric field within capacitor. So I'll have electric field lines that look like that, pointing from the positive charge to the negative charge. And everywhere in the region with between the two capacitors, uh, the electric field would be constant. And remember, we get that from drawing that Gaussian surface over there. So yeah, this should be a pretty standard problem. Let's move on to the next one. Yeah, use Gauss's law. Oh yeah, use Gauss's law to determine the magnitude of the electric field between the plates. Calculate the electric potential V between the two plates. Calculate the capacitance of the capacitor. Uh, don't worry about the specific numbers that they gave you. Just use the variable sigma, uh, A, uh, D, and yeah, yeah. You don't have to worry about the exact values. Just like just just keep those like variables. Yeah, when you're uh writing your equations. So I'll give you guys some more time to do this. It should we did go over it in the beginning of class, but it should serve as a helpful review. So yeah. All right, I'll go over this for time's sake because we're running low on time. So um I'll draw a side view of uh, the two plates. So this is my first plate. Oops. Or okay, I'll just use the diagram in the last page. Okay, so these are our two plates, and we're assuming they're infinite plates. So, um, if I okay, first, the reason why there is no electric field that's outside of the two plates is remember because these two are infinite plates. If I have like remember that when we were doing this when in the first class when we were learning about Gauss's law. So, if I had a positively charged plate. Let's say it has sigma, right? It has charge density sigma, then the electric field lines will be looking like that, right? Uh, and remember that when we use Gauss's law, we found that there were the two electric the electric field it was actually equal everywhere in space. So if I draw this Gaussian surface, so this is like or okay, I'll draw it a bit better. So like this. and this has area A. So uh, like there's flux through the left part and the right part, and if this is a cylinder, there's no flux that goes through the side of the cylinder. So I know that uh, E times E times 2A, right? That equals to the sigma, the charge enclosed, or epsilon zero. So sigma A divided by epsilon zero. So E is equal to sigma over 2 epsilon zero. And notice there's no dependence on the distance from the plate. And so if I look at this plate over here, it's going to produce electric field lines like that way. And like, wait, I'll draw it again. Like if I'm looking at a point over here, due to this plate over here, there'll be electric field pointing in that direction. Now, sorry, in that direction, due to this plate over here, there will be an electric field pointing exactly in the opposite direction, and also it's exactly the opposite magnitude, uh, because these are two infinite plates. So in the region outside of the two capacitors, the capacitor, there's zero electric field. Now, there's only electric field within the region between the two capacitors, and if I draw this Gaussian surface over here, then I know that I have E. Remember, this is the what the electric field lines look like, and like so on. Like everywhere along the conductor, it's like that. So E times the A, that equals to the sigma A over epsilon zero. So that means E would be equal to sigma over E equals to sigma over epsilon zero. So we've solved the part B, which is finding the electric field in the region within the plates. Now we want to find the potential difference between the two plates. Well, we know that uh, V equals, for a constant electric field, it's equals negative Q E Q sorry V equals negative E times the D, or if I'm looking at the magnitude of the potential difference, then it's just positive ED, like absolute value. So then, I already found E, right? So V would be equal to sigma D over the epsilon zero. Now, okay, so that solves part C. And then I want to find the capacitance, right? So V would be equal to Q over C, right? So C, so that means that C would equal to the Q over V, right? And what is Q? Q is the total charge uh on each plate of the capacitor. So that would be equal to sigma times the total area of each plate. So the capacitance would be equal to sigma A over sigma D over epsilon zero. So we're getting equals to epsilon zero A divided by the distance between the plates. Yeah, that's our formula for capacitance. Right, let's move on. Dielectric, oh, I see. A dielectric with kappa equals 2.00. It's now inserted between the isolated plates while the same amount of charge Q remains on each plate. By the way, what this means is like instead of so now epsilon, so epsilon would now equal to kappa times your epsilon kappa times the epsilon zero. Calculate the new capacitance of the system with the dielectric between the two plates. Electric field strength as what? Electric potential, energy. How would your answers to FG E change if the dielectric had been inserted while the voltage supply was still connected to the capacitor. Right. I'll go over the first I'll go over a bit of this problem and I'll probably leave some of it as homework so that you guys can think about it more because we're running kind of low on time. So calculate the new capacitance of the system with the dielectric between the plates. Okay, so no, we have epsilon equals kappa times epsilon zero. We originally had C equals to epsilon zero A over D. So this is the C old. So the new C, so like C new, like with the dielectric, instead of having epsilon zero, I put kappa times epsilon zero. And I know kappa is 2, right? So C new would be 2 epsilon zero A divided by the D. That is our new capacitance. Now, electric field strength between the plates has what? Electric potential between the plates has what? Energy stored in the capacitor has what? And so on. Okay, so I'll do part F first, and I'll let you guys try to figure out G, H, and I. So these are our plates. This is my dielectric, which is an insulator. So, oh shoot. Okay, let me draw that a bit better. Okay. Okay, so I have a charge Q over here and a charge negative Q over here. Now, the dielectric is an insulator. So what that means is that charges in the dielectric, they're not free to move, but they're able to, so for example, in an insulator, I have negative and positive charge. They're like coupled together. So they're not free to move, but this like the two charges, they're able to rotate. So, for example, if I had this was my negative charge and this was my positive charge, and I placed a really big positive charge over here, what the what this like couple of positive and negative charges would do is it will rotate, and what it will rotate into this configuration. So the negative is attracted to the positive charge, right? So the final configuration would look like this. So similarly over here, when we return back to the parallel plate case, uh, what happens is that there's a negative charge here and a positive charge here. They're coupled together and they'll all rotate so that the negative charge is facing the positive plate and the positive charge is facing the negative plate, right? And so on, like throughout the capacitor. So, over here, it will look like this and this. So what this does is you can see that the positive charges, they're more like the positive charges are more towards the bottom and the negative charges more towards the top. And what that does is it creates an electric field this way within the two plates. And so what that does is it weakens the electric field between the plates. So the answer to that part would be that the electric field decreases. Parts G, H, and I, I'll let you guys figure that out on your own and I'll add it to the homework and yeah, we'll go over it next class. But so yeah, that just concludes our class today. It was on capacitors and conductors. Make sure you review the recording and try to attempt some of the homework problems if possible. I know that this class might have been a bit difficult, especially if these concepts are unfamiliar to you. So if you have any questions, just send us an email or there are always resources online that you can look for. And there are some pretty good textbooks that you can reference, like the ones that I sent to you in my first email. So yeah, that concludes our class. Have a nice day.